Okay, I want to start by reviewing the rational functions and their graphs. Chapter 9, Section 3. Definition of a rational function. A rational function is a function that can be written as f of x is p of x divided by q of x, where p of x and q of x are polynomial functions, and q of x is not equal to 0. Remember, denominator of a fraction cannot be 0. Denominator, denominator of a fraction cannot be 0. And that's all this is saying right here. Where p and q are polynomial functions and q of x is not 0. So we start with a rational function where we have a function on the top, a function on the bottom of a fraction. For example, we could have 2x over x squared minus 4, polynomial function. We could have 7x squared minus 3x plus 4 over x minus 6, polynomial function. As long as we have the caveat, x cannot equal 6, called a restriction. Or down here, x cannot equal positive or negative 2, because either of those would make this 0. This would make this 0, and that's what we're saying when we write the definition. All right, so here we have a function, negative 2x divided by x squared plus 1. Now it says, notice there's no value of x that makes the denominator 0. Remember, x squared plus 1 is equal to 0, so x squared is negative 1. If we take the square root, we get x is plus or minus I, but I is not real. And we're only dealing with real numbers right now. So notice there's no value of x that makes the denominator 0. We call this a continuous function because it doesn't jump, break, or have holes in it. So it says it can be drawn with a pencil that never leaves the paper. So let's do that. I can trace this function. Oops, sorry, I lifted my pencil because I needed to see where I was going. And I didn't have to lift my pencil to draw the function. So far, so good. Continuous means just that. I can draw it without lifting my pencil. Let's see what a non-continuous or discontinuous. Okay. Again, we start with what we talked about at the beginning. X squared minus 4 is equal to 0. When is that true? Well, it's true when x squared is equal to 4. I take the square root. It's true when x is plus or minus 2. Wait a minute. This is the graph. The x can't be plus or minus 2. And we draw those like this. And they have a special name. They're called asymptotes. A-S-Y-M-P-T-O-T-E-S. Okay, notice how the graph jumps over those. I can draw this piece over here without lifting my pencil. But to draw this piece, I have to pick up my pencil, come all the way down here to draw this piece. Then I have to pick up my pencil again to come all the way up here so I can draw this piece. These two dotted lines are called asymptotes, and asymptotes are the places where we have discontinuities or discontinuous parts of the function. That's where the function can't go. Asymptotes, I call them the curbs. Like curbs on the street. You shouldn't cross them. Okay, jumping the curb is not safe with your car. It's not a good thing to do. So be careful. Don't jump the curbs. All right. So this is another graph. We take a look at the function. We start with the denominator. Remember, we always start here. We make it equal to 0. That will be 0 when x is negative 1. Wait, that's what it says. X can't be negative 1. And negative 1 is right here, according to my graph. Okay, so I can draw this piece over here, which is going to get closer and closer to there. Then I'm going to pick it up clear down here, and I'm going to bring it up. I'm going to grab a hold. Oh, bad drawing. And there's that one. Ew, that was really bad, but you get the idea. So this is also a discontinuous graph. It has a discontinuity. All right, the second and third graphs have what are called points of discontinuity. So to find these points, find the values that make the x of the denominator 0. So whatever makes the denominator 0. So let me find you a function here. Hold on one second. How about this one? Okay, all I care about is the denominator. So I take the denominator, I make it equal to 0. That was a bad choice. I should have, that's okay. And then I take the square root of both sides. So I have 2 points of discontinuity. If I have something like this, I take the denominator, I make it equal to 0. My discontinuity is when x equals 4. Here is when x equals plus or minus 5. Here is when x equals 4. Whatever makes my denominator equal to 0. That is what we're going to do. Okay. Moving on. Vertical asymptote. The rational function p of x over q of x has a point of discontinuity for each real 0 of the denominator. Now it says if p of x and q of x have no common real zeros, then the graph has a vertical asymptote where there's a 0. If p of x and q of x have a common 0, then there is a hole in the graph, or a vertical asymptote. And we'll talk about the difference between those two. So here we go. Let's see how this works. Okay, we take the denominator, we make it equal to 0. X minus 2 times x minus 3 equals 0. The 0 product property comes along and says if the product is 0, then one of the factors must be 0. Okay, that gives me x equals 2. That gives me x equals 3. We're good so far. Okay, now we need to check the top. So we take the numerator and make it equal to 0. And we ask ourselves, do these match that one? The answer is no. So there are no common zeros. No common zeros. So that means there's a vertical asymptote at 2 and at 3. So there's a vertical asymptote right here and another one right there. Again, they're vertical asymptotes because they have nothing in common with the numerator. Let's do that again. Okay, take a look. I do the numerator. I have a 0. So x equals 2. I have another 0. X equals 1. I go to the denominator. So x equals 2. Wait a minute. They both have an x equals 2. So there's a hole in the graph. Your calculator won't be able to show you that hole, but you can simply go to the table function. And when you get to x equals 2, you will have in the y equals column, it will say error, meaning it can't find a value. Okay, there are no vertical asymptotes because there's only one 0 in the denominator. The 2 in the numerator we're only looking for matches. We're not looking for anything else. Let's see what else we got. Okay, let's take a look at this one. Okay, if I take the numerator, I have x equals 3. I have x equals -4. I look at the denominator, I have x equals 3. I have another x equals 3, and I have an x equals -4. Okay, so I have a pair of these, so that makes a whole. All right, I have a pair here, which makes a whole, but then this guy comes along and says, hold on a minute, because I have an extra one in the bottom, it makes an asymptote. Okay, the vertical asymptote then is at 3. Okay, now your calculator, if you're using your graphing calculator, is going to try to draw those lines. Don't freak out, it does some weird stuff. Let me know if you have some issues and I'll help you look at it and take a peek. Okay, so that takes us to the last section of horizontal asymptotes. And I tried really hard to highlight, but my highlighting didn't come through very well. Okay, there are 3 rules. First of all, read this one very carefully. It says at most 1 horizontal asymptote. So it doesn't have to have 1. It could be 0 or it could be 1. You could have this many. Okay, so it says the first rule, and I'm going to try to mark these. Rule number 1. It has a horizontal asymptote at y equals 0 if the degree of the denominator is bigger than the degree of the numerator. So, an example of that, if I have x plus 3 over x squared minus 2, this has a degree of 2, this has a degree of 1, this is bigger than that, so the answer is there's a horizontal asymptote at y equals 0. The degree, remember, is the biggest exponent. Degree equals biggest exponent. Degree equals biggest exponent. Okay, rule number 2 starts right here. It says if the degree of the numerator and the degree of the denominator are equal, x cubed plus 4 over x cubed minus 6 both have a 3. Oops, sorry about that. Let me move it over a little bit. There you go. Then the graph has a horizontal asymptote at a over b. A is right here. B is right here. It's the coefficient of that term. So in this case, it would be 1 over 1 or 1. If I had 3x squared minus 2 over 7x squared plus 4, again, the exponents match. Then I would take the 3 from the top and the 7 from the bottom, and that would be my horizontal asymptote. My third rule is right here. It says if the degree of the numerator is greater than the degree of the denominator, then there isn't one. So if I have x squared over x minus 1, there isn't one. None. There aren't any, because it's the degree of the numerator is greater than the degree of the denominator. Okay, let's see how that applies. Oh, and I have a whole bunch of pages that say the same thing. Here we go. Here's one. We have, here, let me rewrite it. Hold on a second here. we have 4x over x cubed minus 4x equals y. All right, first of all, we take a look. What's the degree of the numerator? It's 1. What's the degree of the denominator? It's 3. Okay, so the rule says if the degree of the denominator is greater than the degree of the numerator, go back, the denominator greater than the numerator, we have a horizontal asymptote at y equals 0. Just like that. Okay, while we're here, let's talk about those vertical ones because we're going to have to anyway. Okay, so we take a look. This one has a 0 at 0 because when 4x is equal to 0, x is equal to 0. So we have a 0 on the top at 0. The bottom, we have x cubed minus 4x. We take out an x. It's x squared minus 4. Okay. So we have x equals 0, and we have x squared minus 4 equals 0. So x squared is 4. Okay, so we have a 0, and we have a plus or minus 2, which means this makes a whole, and these are vertical asymptotes. Oh my goodness, so what do we have? What in the heck does this look like? Well, let's take a look. It looks like this. First of all, we have a horizontal asymptote at -2. We have a horizontal asymptote at 2. We have a vertical asymptote. I'm sorry, I have this totally backward. Vertical asymptote at 2 and a vertical asymptote at -2. We have a horizontal asymptote at 0. And we'll get to the whole in a minute because I can't really draw that. So here goes. This is what the graph looks like, and I do this on my graphing calculator. I can see that it does this. It does this. And it does this. And guess what? When I get to here, I draw a circle around it to create the hole. And that is what my graph will look like. That's pretty crazy if you ask me. Let's try that again. I have one more equation. Let me get the right page going here. Alrighty. Okay, so if I have the equation, okay, first of all, I ask myself, what's the degree of the numerator? It's 1. The exponent is 1. What's the degree of the denominator? It happens to be 2. Exponent is 2. Okay, when the denominator is bigger than the numerator, my answer is y equals 0. Sorry, not 1, but 0. Y equals 0. Once I have that, then I am able to take a look at the top. 3x equals 0, so x equals 0. And x plus 2 equals 0, and x plus 2 equals 0 results in x equals -2 twice. Which just means I have a vertical asymptote at -2. Don't let that freak you out. Alright, so what does this one look like? Well, here's -2, because I said so. Here's 0. We have an asymptote here. And this graph does this. And, ooh, this one's kind of funky. Like so. There are no holes, so I don't have to worry about drawing any of that. Okay, so I know that some of you have that worksheet still out there. I'd like for you to do the best you can, see what you can come up with, and try to submit. Again, if you have questions, let me know. We'll take a look. And best of luck on this one.